Record. Okay, welcome everyone to the second week of our hands-on GeoAI course, to the second lecture. This week will be on basics of machine learning. Our lecturer today is Shuprashanka Dey, Dr. Shuprashanka Dey from Aalto University. Just a quick update with three general announcements. For those of you studying at TU Graz, please make sure to finish our registration with the CSC. We can see in the project that many of you are still in the process of creating your accounts, so this will help you a lot in the practical part. Second thing is about the assignments. We have assignment 1 that we will advertise this week, which is basically based on basics of machine learning lecture, which you will hear today. And the group assignment will also advertise the first steps this week, where we will ask you to do a self-assessment questionnaire based on your skills and preferences and so on. So this will give us more information to divide you into pretty equalized groups between TU Graz and Aalto University. So be on the lookout on Slack. Probably I will send a reminder also on the email, so we'll keep everything simple. Slack and website for the information. Email will be sent out just for a reminder to look the new information up. And now Shuprashanka will give you the lecture.
Okay, thank you, Ivan. So, hello from Aalto. So we will start with the very basic of the machine learning course. Few practicalities before I start to the main content is that as you know, like machine learning is a very broad topic and we are entitled to cover in one lecture here. So pardon me if I miss something, but what I try to do here is like try to make it as visual as possible. So try to cover it so that you can revisit and then you can go back and you can check the visualizations are clear for you or not. Please use the textbooks and the reference materials that I have listed there at the end of the presentation. And so here I'll try to at least build the intuition behind the main ideas. And if some part of those are based on heavier maths, I'll probably skip them, but I will encourage you to read them from the textbooks and then probably revisit the slides if that helps you. And yeah, I have mostly try to make it like a visual one, but this is the first time I'm teaching this course, so your feedback will be very helpful. And thank you very much. Please share your feedback after the course. Thanks for learning with me. So let's start. This is something last week Ivan have been talking about. So machine learning is a computer program. There are three main aspects of it. One is experience for some task T, and there is a performance measure about the performance by the machine. So for example, we can have some data. As you can see here, there can be one data of elevation of a terrain, and there is another data from river distance from where you are located, and based on those two data you can predict whether you are in a flood risk zone or a flood safe zone. So it's a very basic tabular data that often we start in a simple machine learning problem. So how humans normally solve this problem, they come up with some rules. So if my elevation is some less than 5, my distance is less than 5, then probability is that I'm standing in a flood risk zone. But the machine, of course, does the same, but they have a framework for that, and that framework is the experience, where we gather a lot of those data or such tables like historical data, and then we do a prediction of what is the possibility of the then we do a prediction about predicting the flood, and then we measure how correctly or well this machine is classifying that. So typically the idea is that more experience comes with better performance. So here is one simple visualization. You can think of that in the top of in the right figure in the top, you see there are two levels. One is blue, one is red, and as in the x-axis there is this elevation, and the y-axis there is this distance to the river. And as we are getting more data with time, our machine is typically learning that decision boundary of the flood risk and the safe zone in the middle figure. And as we do that, we gradually it decrease our error. So this is basically typically the whole framework. So in the top we have the experience, in the middle we have the task of learning the boundary rule, and in the bottom we have the performance measure. So as we have more data, you can see our gradually our performance starts improving. Okay, so next is that there are two types of approach. Sorry, I think there is some reason. Yeah. So basically, there are two types of machine learning algorithms exist. One is the supervised learning, another is the unsupervised learning. And in the supervised learning, we provide the training data. We also provide the target labels. And in the unsupervised learning, we don't provide the target labels. That's the basic difference. And this is something we can visually see, that in the top figure where we already know the data labels in two different colors. But in the bottom, we didn't, if you see in the beginning of the animation, there was no such labels. So in the top, we had already classified which are flood risk zone and which are safe zones. But in the bottom, this is something that the machine is trying to learn based on some algorithm. So the idea is that in the supervised learning, we already have the labels available. In unsupervised learning, we don't have the labels available. And that's what the machine tried to do. Okay, so this is some broad overview. Let's see what a supervised learning and how actually it looks in more detail. So basically there are two types of tasks that a supervised machine learning do. One is called a classification task, and the main idea is to predict discrete categories or labels. So here, for example, the example that we are seeing, it's a classification task where we try to map a zone either to a flood risk or a safe zone. And there is another type of task called a regression task, where we are try to predict a continuous quantity or a number. So for example, based on the size of a house, we try to estimate the cost of that house. And typically the idea is to first we try to understand the regression problem with some examples, and then we will go to the classification problem. So here is the basic regression setup. In the rightmost top figure, I am actually enlisting the data there. So based on the size, you have one price value. You can see 50, 140, 75. I have colored them. And this is what I was referring about the labels. So basically we have some input as a size and an output and price. And if we just plot them in a space where in the x-axis you have the size of the house and in the y-axis you have the price of the house, you can actually match the color. So those data points are actually plot there. Now what the regression tries to do is, for any unknown numbers, for example, in this figure, in the top figure, you can see this for the size of a house as 85 and 135, there are question marks. So we don't know what will be the price for those houses of those size. And if we want to predict the prices of those size, then we want to estimate based on the data that already are given. So the basic goal is that we have these features as the size of the house, and we have the target as the price of the house, and our goal is to find a mathematical relationship between this feature and the target. And because these targets are given in the database, these are called label data. That's what we are learning about the supervised machine learning algorithm. So this regression is a supervised learning because the price or the labels are given, and we now want to estimate what would be the price for the 85 and 135. Those are marked with the question marks. Let's quickly see how this thing works. So basically, this is the overview of the regression flow. And what we are seeing in the earlier diagram, there was this training data set. So basically, without the question marks, the rest of the data is the training data set. And then what we try to predict is the new unseen data, that is basically the question mark data. And in the right side, this is the diagram where, based on the historical experience, we try to feed a learning algorithm, and that is the training phase of that part. And now when we have the unseen data, we use the same learning algorithm to predict the output. And this might be a little bit confusing, but let's see how it does, and as an example. So here what we try to do, because this is a two-dimensional space, there is one feature and one output. So we can model this as a straight line. And how we draw a straight line in a two-dimensional space, from our class 2 mathematics, it's given by this equation. So basically this omega naught is the intercept of the straight line, and omega 1 or the w1 is the slope of the straight line. And if we do that, then we can see if we can come up with such a line, then we can actually get the values of this question mark data if we project them on the straight line. So the goal is there, how we can find this straight line, and this straight line can be then formulated by this equation where it has two parameters, this omega, this w0 and w1, and based on those two parameters we can then put the x1 value there and get the estimated y value there. So what possibly it can happen is that this straight line can have different shapes. So for example, there are two such situations, so where we can have the straight line such that this is the optimal fit, but we can also have a different type of straight lines. So how we know which one is the best fit for our model? And that's where this idea of sum squared error comes into the picture. So what is sum squared error? The sum squared error is the error from each data point, how much you are deviating for each of your input points. So as you can see, we calculate for in the left animation or in the right animation, for each data point we calculate based on that equation on the top, what is the error there. And you can see that total error in the left plot is actually less than the right plot. So we can say that the left one is a better fit than the right one. Now why we are interested at all about this sum squared error loss? Because this is something, because the machine cannot see or visualize which which line is the best fit here. What they can actually know about the quantitative values. So they actually calculate this mean squared loss, or the sum squared loss rather, for each of such straight line possible, and then they try to find which one has the less amount of sum squared loss. So how they do it? So here is a bit complicated figure, but let's break it down one by one. So in the left, as you can see, we have the same training data. In the left, in the matrix format, we have the same training data. So we have the size of the house, and in the right, we have the price of the house. And we can show that in the right side, in the data space, where there are multiple such line exist that can probably fit the whole one, and the dotted line there is the best fit. But how we know which one is the best fit? And that how we do by putting different values in the W0 and the W1. So you can see that whenever this W0 and W1 changes, the line is kind of changing in the figure number 2. So see the figure number 3 in the bottom left, you see the W0 and W1 is changing there, and that is actually causing the change in the figure number 2. And now in the figure number 4, we are talking about a different space. So basically what we are doing here in the figure number 2, we are talking about a feature and target space. And in the figure number 4, we are talking about this W0 and W1 space. What is the meaning of that? So one point in the figure number 4 is actually reflecting one line in the figure number 2. So you can think as the values of W0 and W1 are changing as a point in figure number 4, that is actually changing the line in the figure number 2. And this is very important, because whatever value you get from the figure number 4 is actually deciding the fit in the whole data. So you can think of something like that. These W0 and W1s are very important to understand which one is the best fit in our model. And then we call these W0 and W1s as the weights of the model. So how we now identify, for example, here you can see at this animation ends at certain value, which is the optimal fit. So how we find these optimal weights? This is the very crucial and important question in the machine learning. So basically in the machine learning, what is the goal for most of the algorithms? They try to find the optimal weights that the machine can learn from the data, and then they will use those weights for the unseen data to estimate those values. So if you have any questions, I think I have talked a lot here, but if you have any questions, you are free to ask. If I'm going a bit fast, please stop me and raise your questions if you have any, or I'll continue to the next slide, because this is something important. I want you to understand these weights are important to find the optimal fit here. So do you have any questions so far, or is it a bit clear? Okay. In Graz side, do you have any questions?
So no questions for now. It's all clear to the students.
Okay, thank you. Okay, so now there comes this idea of loss landscape. And what is this loss landscape? So basically, as we are seeing, these weights, according to the value, there is the sum squared error loss function that I was showing. And this basically in the left, it basically creates a three-dimensional plot. So depending on the weights, we will get different loss value. And that loss value, we want to minimize the loss value. And in the left, you can see as for different values, pairs of the weights, we are getting a different point in this valley. And in the right, I have shown that in a contour plot. And our goal is to find the optimal fit by going to the lowest point of that value. And this is something we do in optimization. It's the concept of local maxima or local minima. So basically, this is the minimum point. We try to find where the loss function is actually the lowest. And if you are interested, there is very nice books on optimization. I have listed in the reference list. Please try to see that and revisit that concept. It's a book by Glassner, and it has like nicely shown this visual concept there. Okay, so the basic idea is that we try to find out the values of the weight so that our loss have been minimized and such that we can get the suboptimal fit. And here is the basically the vector notation of that. So we have we arrange them in a vector form. So there are this weight W0 and W1, and we have the size of the house that we can arrange as a column matrix, and if we multiply them, we get the predicted value. And this is the loss function that we are talking about. So this is the sum squared error. So in the y, so for each of the sample in the training data, we have the real value, the yi, and the predicted value, the y hat I. And if we take the square of them and sum them, we get the total loss that I was showing in the earlier visualization. And then how we find the minimum point, and that's where this gradient descent algorithm comes into the picture. I will not go into the detail, but basically the value that I was showing, and there was this bottom point that we are trying to go. This is the mathematics behind that, the way we go there. So how we do that? Basically, we try to find, so whenever we want to find a minimum of a function, we normally take a derivative of that. But here, this is a two-dimensional space, so we have to take a gradient of that. So understand this concept of gradient here, because we have two weights, W0 and W1. So this is a two-dimensional space where we need to go there, and that's why this gradient thing comes into the picture. And our idea is to find the point where the gradient is the lowest. So this is something I will encourage you to revisit, but basically this is just taking derivative with respect to the W0, the one weight bias, and the another weight, the slope. And then we find something like this, and then we update that with the new weights. So to summarize everything in one picture, this is the way. So we if we want to find this in the left figure, if we want to find the optimal weight that is written as the star, we do that by several number of iterations. And how we do that? We start with a very random point and we calculate the gradient vector, and that gives us that which direction we have to tune our weights, and then we adjust our weights and we update this parameter. So there are these 5 steps you can see in the right. So at each iteration, we find out where exactly are we in the weight space, and we put those in the gradient formula that I have shown in the earlier slide, and then we find the gradient vector, and then we calculate the which direction we should go, and then we update the new parameters. So this is the basically the visualization of the gradient descent. And this gradient descent is very much important in machine learning, because this is the way the most of the algorithms learn their weights. And it has different type of variations, but the idea is that we have this space where we have the weights in the independent axis, and we have the loss function as a function of those weights, and we try to minimize that loss function. And what is the loss function here? The loss function here is the sum squared error that we were showing here. So yeah, so basically I would encourage you to revisit the whole gradient descent from the first slide, and then if you will be able to understand what exactly is happening. But to summarize that, then once we find the minimum point, we come up with these parameters, these weight parameters, and those parameters are then used to estimate the new data. So here, for example, if you remember, I showed some question mark, and those are the question mark data point that we didn't have the data in the training data. And now once we find the weights from the gradient descent, we can plot the optimal line there, and then we can actually predict what would be the model output. So you can see in the top right, there is the train parameters that we get from the gradient descent. Then we can do the predictions from that data based on that model, and that is the final decision rule in this y hat equal to 26.4 plus 2.57 into x, and that is what our model actually have been learning. So this is the very basic idea of gradient descent, and because I was discussing it in using one variable, you can now expand this into two variables. So for example, we had only the size of the house and the price of the house as the output. Now let's add bedrooms, number of bedrooms as one variable. So you can see that two-dimensional plot is now becoming a three-dimensional plot, and this is true for d-dimensional plot, but unfortunately we human cannot visualize in the more than three-dimensional plots. But in the two-dimensional plot, we get the straight line for the linear regression, and in the three-dimensional plot we get the plane as the linear as the plane where we try to fit the data. So the vector form remains the same. The equation, as you can see, is been expanded to the d-dimensional space. The rest of the things remain the same. Only the gradient vector now will have more number of vectors. So it was initially we had two weights, W0 and W1. Now you can see there are D weights. So the number of features you have is typically the number of weights you have, plus you will have an extra weight W0, which is the bias, which will be remain there. So this is more like the idea of a d-dimensional space. So far we are talking about the straight line feed to the data. Now let's come back to the one-dimensional case where we have one input feature and one output feature. And now let's imagine that the price of the house doesn't depend like a very straight line. It has a more like a curvy line or a very non-linear feature. So how we can then fit a straight line? It's not that easy, right? Because it doesn't look like a straight line would do a job. So in that cases, we do a polynomial regression. And what we do to do the polynomial regression, we change the feature transformation. So instead of using just one W0 and W1x, we add the polynomial part along with it. So here, for example, we are using a cubic hypothesis. In the second point, you can see that the y hat is been now expanded to W2 into x square and W3 into x cube. So we have increased our weights from W0, W1 to W2, W3. And why it is still linear? Because we are adding them as a linear combinations. The only thing is changing that. So we had one input feature, and we are taking that square and cube and adding them with different number of weights. And the rest of the idea remains the same. We similarly calculate the loss. We similarly update the new weights while doing the gradient descent. And then as a result, we will eventually get this pattern. So how it does that? So basically, this is one of the animation when we try to see that what is the different type of polynomial degree we can use for that. So for example, here we are using the 3 up to cube. We can stop it in square. We can stop it here like this part. We can stop it in weight into square, and we can also expand into x to the power 4 or x to the power 5. So that is something what I try to show here. So in the right side, I am showing the model complexity. If I increase the polynomial degree, how the fit in the left side will look. So you can see as we can increase the model complexity, the feet of the line starts to be more like curvy, and depending on that, the sum squared error will be different. Now here, one thing to notice is that there are two types of data points. One is the training data, which are shown as the red dots. Another is the test data. So the data that the model didn't see yet, that will be, rather we will use to predict their values. So when we do the training, and there are two types of losses actually. So one is the training loss, another is the test loss. So the training loss is whenever we are estimating the sum squared error from the training data points only, and the test loss is whenever we are calculating the loss from the test data points. So what we can see here, as the model complexity increases, so the training loss in the red line, it's getting decreased. So if you pay attention, so the training loss, the red line, you see it is going down, but the test loss is actually went down, and after that it starts increasing. And this is something very crucial when we design any machine learning algorithm. So there is a concept called bias variance trade-off, and what that concept tells us that, so we of course have the possibility to increase the model complexity. We can make it very sophisticated, but not necessarily that will give us very good results. Why so? Because we can see that if we want to fit the very high order polynomial features here, our model is performing very well in the training data, but because it didn't see the test data yet, it doesn't know how it will perform for the test data. So whenever it sees the test data again, the error or the fit doesn't work well. So this is, I am actually covering a very broad topic in a very short time. I would recommend you to visit this concept. There are very nice materials also covered in the book. But the idea is that, the basic idea is that if you increase your model complexity, that doesn't give you the good model all the time or the best model all the time. So we need to come up with a trade-off or a particular point of interest where our model complexity is not so high, yet we are achieving good results. And this concept is known as the bias variance trade-off. So as we were seeing that, so this actually leads to two issues. One is that if our model is too shallow or too naive or too easy, it gives us underfitting, and if the model is too complicated or too sophisticated, it gives us overfitting, and that I'll actually going to cover in the next slide. So there is a concept called regularization in the regression problems, and this regularization concept actually helps us to prevent the model to do this overfitting. And you can see that in the left figure, there is this this looks like an overfitted one, because it is performing very well in the training data, but as long as you have the test data, it will provide you less number of error. So the idea is that in regularization we add a penalty factor. So the loss function is actually been modified along with the sum squared error with a penalty factor, and that penalty factor will not allow the model to overfit more. So it will create some sort of error, additional error in the model, so that you don't, even if you build a very sophisticated model, this will not allow you to gain much overfitting. And that's how we normally use the regularization and also use a sort of sophisticated model. So there are basically two popular regularization concepts exist. One is called the ridge regression, another is called the lasso regression, and there are the formulas there. So we will see more this in the tutorial part. It's quite easy to implement this, but here is the idea that I want you to learn is that in both of these regressions, they have their pros and cons. Normally, this is just adding the weight square in the ridge regression and with the penalty factor. And this in the lasso regression, we normally just weight the norm of that one. So the degree 1 norm. And we will see how to implement this ridge regression and whether this helps or not in the tutorial. Okay, so far we have covered some regression problem. If you have any questions, you are encouraged to ask, or I am talking too fast. Just let me know. Ivan, do you have any questions from that side?
No, doesn't seem like that.
Okay, thanks. Is it okay? Okay. So now we will talk about a little bit classification problems. So what happens is that in the regression problem, we have seen that it is quite good at many cases, but let's imagine this situation. So we have one feature in the x-axis is the elevation feature, and we have a possibility that whether there is a flood or not based on these data points. So the red is that there might not be a flood, and in the blue there might be a flood. And if we get these data points, then it's not easy to fit a straight line. As you can see, it's if you fit a straight line in this data, and then a data in the far blue comes out, then your straight line comes kind of given a very weird shape, and it doesn't telling the story in a way. So in those cases, we come up with a different modeling approach, and and this is a very interesting concept called logistic regression, where we have find a function that try to get the probabilities of the distribution, and this function has some property. So it basically calculates the probability based on this formula shown in this figure. So it's p equal to 1 by 1 plus e to the power minus z, where this z, depending on the value of the z, we will get whether a point will be in 0 or in 1. So this is for a 2-class classification problem, and we use this z equals to the similar way we did it for linear regression. So this z is basically the straight line equation, and instead of the w0 we are using the term bias here, the term b here, just to show that, but this is basically the same straight line that we are talking about, talking in the linear regression. And this gives this sigmoid looking curve. So sometimes it also called the sigmoid function, this s looking curves. And how it does that? So basically there is these steps. There are like for each point it calculates, it has this w and b that you can see. So for each point it calculates some loss. So the basic idea is this, using the same type of gradient descent concept, but here instead of the log function is a probabilistic loss. So if you see in the step 2, there are the steps I have covered there, 1 2 3 4 5, and in each of those the idea is the same. We first calculate a linear score, we calculate the probability, then based on the log function we calculate the loss, we find out the gradient, and we do this iteratively for each such point. And once we do that, we then find out what would be the next best guess for the next weights, and in this way we try to find out the best possible fit for that. So here if you just wait for the last point to be finished, so far it is calculating the average loss in the right, and once it done it will find out the total loss. So here is the final average, and then we find out what would be our new b and new weight, and then it adjusts the sigmoid function. Accordingly, it finds the best fit in this case. So this is like a very small simulation where it shows you like how the optimization steps occur. So with each step we try to estimate the loss, and then we try to minimize the loss, and finally it gets fit in the data. And now once we learn this pattern, we throw the new data in, and then we try to predict the probabilities of the whether the data is in the 1 class or in the 0 class. So once we do that, yeah, so this is the right side, the predicted flood risk, and this is the left side. The right side is the safe zone, and the left side is the predicted flood risk based on the elevation feature. Okay, so logistic regression is good for binary classifications, but there are some problems with the logistic regressions because they try to find out a boundary to separate out those two flood risk and flood safe zones. And how they try to find out, they try to come up with a line here. So now don't confuse this line with the regression line that I was talking to you. So in the regression line, the idea was to fit all the data points with the same line, but here the idea is to come up with a straight line or maybe a curvy line that will actually separate the data points. So here, if you remember in the first example, I was showing you once in the x-axis we have the elevation, in the y-axis we have the distance from the river, and based on that we have the several data points, whether it's a flood risk zone or whether it's a safe zone. And in the classification problem, we are trying to find out that boundary where we can, if we are thrown with a new data point, for example, this big circle here, we can know that whether that region belongs to the flood risk zone or flood safe zone. But the problem is with logistic regression is that it cannot guarantee you whether the separating line is the best fit. So it may so happen that one point comes to the figure and that point actually belongs to the flood safe zone. But because the line is not the optimal one, the model will predict it's a flood risk zone. So there comes the concept of the support vector machines or the SVM, where it try to optimize the safest boundary. And in the right, you can see that this looks a little bit safe because the points in between those width or that street looking thing, there is this possibility of maximum margin. So all the training data point you have, they try to split it as far as possible. And this is something important because in the logistic regression we can have a risky boundary, but in SVM that risky boundary is actually get replaced by the algorithm to come up with a better predictions. And this is the way it try to find the optimal fit, and then it creates a concept called support vectors. And what are those support vectors? As you can see, those highlighted points, so those points are actually in the data, and those data are the most those data are the boundary data, you can say, in a way, and they are the extreme data points in that cluster. And the idea of the support vectors machine is to find such data points and then creates the separation between that, so that it can identify those data points. And you can see there are two dotted lines there, and these dotted lines are called the hard margin because so far there is no possibility of existing any data within that within those red and blue dotted line. But so this is the maths. I will probably ignore this because it will be a little bit complicated to explain right now. But I would recommend you to revisit this. Basically, I have been showing here what are the mathematical equations for those different lines here. So these red and the blue dotted lines are the hard margins. And in the geometrical space, you can actually define them by these equations. And there is a beautiful optimization problem, how we actually find those lines and how we calculate the weight, and then it goes like that. But what is so something I will skip it here. So here is some +2 level mathematics of how that distance is being calculated and how that concept is translated here. If you have any questions, you can ask me in the Slack, and I can probably give you some explanation about that. But what I'm trying to say you here is a very interesting concept. Is that this is a very good situations when this data are separable. So they don't have any like overlaps. We can find these hard margins quite easily by those mathematical equations and those mathematical concepts. But these things become tricky when we have this mixed up data, and then this idea of soft margin comes into the picture. So in the left, you can see now the data are not quite linearly separable, these data of different levels. So what we cannot draw those dotted lines, and even if you draw them, they will look something like the figure in the right. So what happens there is that we now try to at least find a way so that not many data points are within those dotted lines. So if we have very large number of data points there, and then the classification error will be high. So there is this concept of regularization parameter, a C. I will show that in the tutorial how that you can do that. I will encourage you also go to this book that I have listed in the reference. They have explained it in a very nice way, and the visualization. So in this particular situation, we talk about the concept of soft merging, and we try to create that soft merging as narrow as possible so that we can get rid of that error. And then there comes the concept of hinge loss, and basically, so we give every misclassified points and we do this penalty for each of those points that comes into that picture of the dotted line. And now that was when the points were mixed up, the line was not separable. But here comes another tricky situation when we have the decision boundary that is non-linear. So you can see this data points. They are by human eye, it is quite easy to separate them. But how a machine will understand that, because they cannot draw a line among it, they cannot draw a straight line among it, right? So what the machine is, we can do that is that we think of that a way of increasing the dimension. So this is a two-dimensional space. We can increase the dimension in the three-dimensional space so that every point from the center, how far it is, will decide how up it will go. So it's I can show you by an animation. In the left, you can see that this is the center of the square, and if the points are close to the center of the square, they stay where they are. But as you go farther away from the center of the square, the points will go higher. So that is what happening in the right side. And then once you uplift the farther points, the farthest points to the higher or to the above, then you can see there is a possibility to draw a plane between those blue points and the red points. Pardon my colors are a bit counterintuitive. So the red point should be in the middle and the blue point should be in the boundary. But I think you get the idea. So when you have this type of non-linear boundary, the idea is to use a trick called kernel trick, and that kernel trick will gives you an additional dimension where you can pull some outlier or the sum of the peripheral data on the top and keep the central data in the bottom, and then you have a clearly visible plane that you can separate those data points. And this trick is putting these data points to a higher dimensional space is called the kernel trick transformation. And here I have actually enlisted these formulas, and you are encouraged to go through it. There are some real world applications of this linear and non-linear SVM. There are some like basic differences. So for example, the decision boundary in linear SVM is a straight line or hyperplane, but here in non-linear, as we have seen, this is a curved on linear, that is linearly separable. Non-linear SVM non-linearly separable. So the kernel usage is there. Of course, non-linear SVM will be computationally expensive, and then there are some example of use cases. So far we are talking about this different type of classification problem, and I'm sure you have doing this KNN for some time. Probably, I think you guys are familiar with KNN. So I will not take much of your time, just to revise. It's a non-parametric supervised ML algorithm. It does the classification and the regression task. It mostly memorizes the dataset, as we know. And how does it work? It searches for the nearest neighbor based on a parameter called K, and then it does the voting. Like it checks that how many of those belong to which class, and then there are distance space. There are different type of distances can be used. Normally we use the Euclidean distance, that is the most popular one. Also there is a possibility to use the Manhattan distance or Minkowski distance. I will not go there, but here is the basic idea. For different K values, we do the new point, we do the classification in that way. So there are 4 such scenarios in the picture. The way it does the voting, there is a very basic visualization. So for example, if you put K equal to 6, it goes there, it finds which points, and then it do the voting and color it accordingly, which are the best, which is the most vote it get. And one interesting thing is that this cannot be used in the classification problem. KNN also can be used for the regression problem. So how we do that? So basically, for an unknown input feature, if we provide the value of k, for example, here 3 is the nearest neighbor it search for, and then it take the average of the new of those figures. So it is quite like I try to explain it in the visualization, but it's quite straightforward. So KNN can be also used in a regression problem. There are some applications in the GeoAI applications, for example, land cover labeling, spatial interpolation, and local hazard screening. But these are, I think, you guys are already aware of. So we will go for some break. If you have any questions so far, you are welcome to ask me. Or it's completely too heavy.
Yeah, I think it's a good overview that you went through systematically to so many different topics and gave so many examples so students can revisit the slides if they need to get into more detail for something. How long should the break be now, Shupra?
I think we can start from 11. If it's okay.
So that's 10 a.m. our time, so 12-minute break. And then we start from then. You still have a little bit of slides, right? And then
yeah, I have another slides on the decision trees and
okay.
Data processing, then measurements of classifications and PCA, and then we will straight go to the tutorials, hands-on tutorials.
Very good. Then we'll start again from in 12 minutes.
Yeah, we will start in 12 minutes.
Okay. Here we go.
Thank you. Okay, so welcome back. This is the second part of the basic machine learning. I hope this is not that math heavy this time. But we will learn an interesting concept called decision tree. I try to give you some intuitive idea behind it. So basically the decision tree is a rule-based machine learning algorithm where we have a data structure like a tree, and that data structure will decide whenever you see a new data point that doesn't have a label, whether it's a flat risk or flat safe, it will decide based on the rules in the decision tree. So in the left, we are showing the tree structure of our already trained decision tree, and it has in the top, it has a rule called if the elevation is greater than 100 meters, then it will decide whether it will pass the data point to one of its branch, whether to the yes or to the no. And if it's yes, then it will come to another rule, whether it is 50 meters away from the river or not. And based on that, the data, then it will go to the particular, whether it's a safe or a risk zone. And if we want to see it, visualize it mathematically, so there are two features. One is the elevation feature in the x-axis, another is the distance to the river feature in the y-axis. So what it basically does is that it's splitting that data space. So you can see there are two lines. One is the vertical line, vertical black line, and that is drawn in the elevation equal to 100. And that vertical vertical line there is basically corresponding to the first rule. And then there is one horizontal line in the right figure that is corresponding to the distance to the river 50, and that is this line. So if we combine that, the star point is actually lying on the top right quadrant, and that is the part if you travel to the decision tree and you will get there. So a new point where which value is elevation equal to 150 and distance to the river equal to 80, it will pass through the tree and it will then classify like that. So it's a very intuitive, simple algorithm, and we will now show that what are the technical components of a decision tree. So this is like an anatomy. So in the top we had the root node that normally contains the data, and then we have the branches. Theoretically it's more like true and false or yes or no, and then we have another intermediate node or the internal node where we have the subsequent questions, and then we have the leaf node at the end for the final predictions. And this is one, for example, a simple animation where we have three unknown samples. We don't know their what would be their classes. We have their values, and we have already a decision tree in the right. And as you can see that for each of the sample,
it goes to the decision tree and it identifies what value it is in, and then it comes to the leaf node to identify the level. It's a straightforward rule-based way to learn this thing. And here comes the questions like how the tree is now learned, or basically this structure that you see, you can see there are these rules are there in the root node. Feature A greater than 5, feature B less than 2. Now the question is that when we try to learn from the data, from the training data, how we learn those rules, and that is where comes the idea of how a tree is formed or the changing the purity. So the possibility is that as we are discussing that the two-dimensional space, there can be vertical lines or horizontal lines, and that will decide how much or what is the rule exactly there. So here you have a mixed parent node of different type of data points. One is blue circles and red triangles, and you can have the vertical line as shown in the right. You can have the horizontal line as shown in the left, and both can be like provided in the root node as a rule. But you can see that in the right one you have made it almost a perfect split, but in the left you have made it like a very noisy split. So this is something where the concept of entropy comes. I will not go into that, but I will encourage you to read that concept from the book, from the textbook. And basically the idea is that if you have a very pure split, you will have less entropy. If you have a very erroneous split, then you will have a high entropy. And there is a mathematical way to calculate that entropy, and depending on the entropy you are having, the trees are normally try to learn which of the rules they should assign to their leaf nodes. And this is some parameters decide that in the machine learning algorithm called max depth or mean sample split, something like that. I will not go through it here, but we will definitely discuss this in the tutorial, how that thing is done. So to wrap up here, so in the classification tree, as we are showing, then this is in the left we have the classification tree. It tries to classify based, and it try to learn the rule from that one. So for example, here we are showing the feature X is less than 5, then it's blue, it's greater than 5, then it's orange. And similarly we can have regression trees. Together they are called CART, classifications and regression trees. In the right you can see that this similar rule-based thing can be also learned from the data. So we have a very like a non-linear cubical data distribution, and we are developing a very simple tree there. So if the feature or the value of the X is less than 5, then we pick all the points before the vertical line here, and we take an average and we get the horizontal line in blue. So if we can keep adding more leaves, we will make this thing more complicated. But the idea, just to give you the idea, if we take the average, then you can see you will get different values. One is 0.13 and one is 0.24. These two are giving you the vertical lines there. Sorry, the horizontal lines in blue there. So just get this idea that this similar concept can be used for regression, where we are just averaging that based on the rules that we have developed. Do you have any problem understanding this concept so far? Or we are good to go? Okay. So how this thing is related, then we can see that if we have tree with one depth, so this is the concept that I was trying to show, that there we can split the nodes into as much as we can, and that is something called a hyperparameter called depth of a tree. And we in these three figures we are showing different depth of a tree, and you can see that when we have only depth equal to 1, the data space is split into two halves. There is this horizontal line, and when we have two more branches coming out of that in the middle figure, and we can see that there are these three straight lines splitting that data space. And if we keep going on, then the data space is getting divided in this different complicated pattern. And the idea that we try to identify those patterns, and then we get the new data points and then classify based on that. So deeper tree captures complex patterns, but there is a problem with that. Whenever you are putting these deeper trees, there is a chance of overfitting, so that it will not perform well with the unseen data. So yeah, so this is something when we have a very linearly separable data. So what the tree structure cannot actually get you the straight line there. They will try to give you a staircase approximation, because it will either cut the whole data space in a vertical line or a horizontal line. So this is the something you can imagine, like whenever you have a data space like that, you need to have more number of depths in the tree so that your data space can be a staircase approximation like that. So here is the problem. So when you have a data like some mixed up data which is not clearly separable, and you can like build a very large tree, and what the trees will try to do will try to memorize the data, and whenever it will see a new unlabeled data, it will probably not not perform good with that data. Okay. So there are some decision tree strengths and weakness. So yeah, they are like quite white box logic, quite transparent. The scaling is needed. Non-linearity can be tackled, but there are some cons. They are very prone to overfitting, and they might miss the optimal splits in that. So this is the problem with the decision tree, and that's where the idea of ensembles learning comes into the picture. So instead of using one tree as a predictor, we can use a committee of tree, or the wisdom of crowd, where we have multiple trees. We ask them to vote for a particular data point, and whatever the majority says, we decide the data point to be that class. So here in the example, you can see there are 3 trees, and 3 of them will provide different values, or either they can provide the same values or different values for a new sample, and based on their vote we can select what the prediction can be. So how that does, it's like a animation. So we have new query, we have the train, these trees are actually trained from the training data, and each of them predicts the level, and we see there are 3 blue and 2 red, and because by the 3 is greater than 2, so we have the higher voting for the blue ones. Okay, and then there comes another idea called bootstrapping. So this is bootstrapping and aggregating. Actually, bootstrapping is the idea of, so we have one training data in the left, that is some data we can see in, we have 3 features, F1, F2, F3, and the output as Y. We have 5 samples of that, 5 different samples of that, S1, S2, S3, S4, S5. In the bootstrapping idea is that you do the sampling without replacement. So that means that you can create another copy of that same data, but instead of taking all the samples, you can take twice one sample and you can leave some samples. So here I am showing some examples of bootstrapping. So in the bootstrap 1, I have taken sample 2 times. I left sample 3 there and sample 5 there. So there are 4 such samples. And I do that again in the bootstrapping 2 example. I leave the S1 and I leave the S5. I leave the S2, and I am keeping S3, S5 2 times and S1. I hope you can read that. And in the bootstrap 3, I am not duplicating any. I am just keeping S1, S3, S4, S5, and I am leaving S2. The idea here is that you can take such permutations of the samples. You create a multiple number of those training data samples, and then you train the trees, and then you get an voting. And this whole process is called bagging or bootstrap aggregation. So bootstrapping is the idea where you create a copy of the original data, but you can either repeat some samples or either you can leave some samples, so that the impurity in the data set, it gets increased, and it gets more random, and then you train multiple trees after that, and then you take the aggregation on the voting, and you get the concept of bagging. So here we can control the number of bootstraps. So here I am showing you 3 bootstraps. You can use more, and you can also controls the number of trees you are actually going to use. And why this is needed? Because we are going to learn a concept called random forest. So random forest is an ensemble based technique where the bootstrapping concept, the bagging concept is used, but there is another thing along with that have been used. So in the previous slide, as you have noticed, that all the three features, this F1, F2, F3, are equally present in all the bootstraps one. We are only playing with the samples. Either we are keeping the samples or we are leaving out the samples. But in the random forest, what we do, we had, if we originally have 5 features from F1 to F5, we randomly take a sample of that. So in one of the subset, we keep, for example, these 3 samples, and we leave the F3 and F5, and in another case we leave the F2 and F4. So we also get the combination of such features, and then we do the bootstrapping. So before doing the bootstrapping, we do a random selection of features, and that's where the random terms come from. And in random forest, we use many number of trees. That's why the forest term comes from. So there are 2 reasons why this random forest thing comes to the picture. And then once we do these types of bootstrapping and random feature selection, we pass that to the trees, and then we try to estimate what will be the classification of the regression value. And the reason for this doing this random thing is that it gives you slightly weaker training data, but the idea is that we want to get rid of the overfitting thing, because normally this ensemble or decision tree, they will perform very well in the training data, but once they see the unseen data, as you have seen those complicated figures, they will try to overfit, and that's why our test data will not get good results. And that's where this random feature can help us. So we intentionally increase some weaker trees, we intentionally increase some noise in the training, and then we expect that will help us to estimate the test data accuracy better than the training data, and reduce the overfitting. So how it does that? So here is another concept that I want to show before stopping it. So there is concept called boosting, and boosting is another way that helps us to similar like random forest, but it works in a different way. So it also helps to get rid of the overfitting thing. So just focus on these 3 figures. In the left, we have a very distribution of 34 points, and it is not linearly separable. Now just imagine if we take one simple random straight line among it, you will get some points are correctly classified, some points are not correctly classified. And if you just take the ratio of that, how many are correctly classified and how many are not, you will get some accuracy. We will cover this concept of this accuracy and this TPT in the upcoming slides. But here the idea is that we can randomly define a line and then classify, and we can even get the accuracy down. Like we can try to find out that there is another learner where the decision boundary is different, and that learner is based on a tree. You can see that that is not performing very well compared to the random classifier, and we call such learners as weak learners. So just bear with me. What I'm trying to say here, instead of doing a full tree, we can come up with a very small tree. Actually, this is not called a tree. This is called a stump, where we have one root node and one leaf, one branches there. So there are 2 leaves from that root node, and that root node is this is the same figure from the previous slide. In the left we have the tree, we have the stump, and in the right we have the view of how it is splitting the data space. So this is a weak one because it is just barely performing what a random classifier would do. And the idea of boosting here comes to the picture, where we try to improve the classification of this stump. And how we do that? This stump makes some error while doing the predictions here. As you can see, the dotted line, it is classifying lots of the red points in the blue region, and some red points in the blue region, and some blue points in the red region. So we want to identify which points it is making the error, and then we try to give some weight to those points. And how we do that? So here we check for, so for example, you can of course check that we can draw different type of stumps here. In the right side we have a better stump, better accuracy, but our goal is to start with the left one and then slowly going to the right one. So we will not go to the first one, go to the right one straight away. We will go there eventually from starting with the left one. And how we do that? So we do that by this animation that I'm trying to show. So in the first attempt, we have a very poorly performing stump. We identify which are the points they are not correctly classified, and then we assign some weights on that, and depending on that weight, we try to find another tree, another stump of a different boundary. And you can see from the horizontal line, there will be a vertical line after that. Yes, that line. And then similarly, we start improving it, the accuracy. So we start with some weights, and then we combine that to the stump. We mark the errors, and then we reweight the data, and this process goes on. And this is basically the overview of the AdaBoost algorithm. That if you probably heard of this one, this XGBoost, AdaBoost, then this boosting thing. This is the way they work. So how they do that? So here are the first stump, then the second stump, then the third stump, and gradually we start adding those stumps, and you can see in the data splits we are actually creating a better classification. So there is the first horizontal line, then the vertical line, then the vertical line, then the horizontal line. Now you get in the center a square where you can see that these red points are getting classified, and this is something you get in the right figure. So now by slowly improving your stumps, you actually go there where your algorithm is performing better than the initial case. So there are some benefits of such ensemble learning methods. They reduce overfitting that I was talking about. They are better for generalization. They often achieve higher accuracy, and this bias variance trade-off that I was talking about, they also take care of that. And they are quite flexible. Yeah, there is another concept called stacking, which is not scope of this lecture at least, but you are encouraged to check that. So basically we have covered this bagging, boosting, stacking, and voting. We didn't cover the stacking, but you are encouraged to learn that from the textbook. But basically the bagging is parallel, boosting is sequential, and with that I will end the ensemble methods. Here we will cover two important topics before we jump to the tutorial. But if you have any questions, quickly you can raise your hands or ask if some part is clear or not. Okay, so let's quickly discuss about some measurement, performance measure. So as we are doing a lot of this classification work, we are trying to identify the decision boundary. Now, how we know like which decision boundary is good, which decision boundary is bad. For example, here the decision boundary is actually classifying the reds and the greens quite nicely in the right figure. But let's look at a different situation when we have mixture of such decision boundary. It is not actually classifying the reds accurately or the greens accurately. How we know that this decision boundary is comparable with some other decision boundary in the same data space? So once the decision boundary is drawn, we can think about four concepts called true positive, false negatives, and true negatives, and I will explain them in the next slide. But let's understand that we can draw the same figure in the left to the right, where we have now just arranged the greens and the reds, and you can see that two reds, they are not supposed to be in the green side, and there are four greens, they are not supposed to be in the red side. And there comes the concept of true positive, false positive. So true positive means when we have successfully identified the green in the green zone, and true negatives are when we are successfully identifying the red in the red zone. But when we have incorrectly classified some of the red points in the green zone, then that becomes the false positive. And when we have incorrectly classified some green points in the red zone, that becomes the false negatives. And this is something in the right side, we call this a confusion matrix, and where we in the actual value we can see in the left side, and in the predicted value we can check that whether, so we are expecting the actual value to be greens on the red side, but there are 4 of such greens which actually goes to the red side, and that's where that they become the false negative. So let me explain that with one example. So let's say there are some figures, some toys, and we are trying to, so this one type of glass is called back glass face. I actually take this example from the book. So these are some historical notation of that looking glasses, but that round shaped glasses is not a Mac glass face, but somehow your algorithm have identified that one in that figure, and that becomes a false positive, and the rest of the figures are correct, but we were only expecting those 2 Mac glass faces in that classification, but because that other glass also got included, it became a false positive one. Okay, and then we have similarly we have false negatives. If we have 2 classes, for example, eyes are present, eyes are not present, and you see this one toy coming into the picture which has eyes, so this is clearly in the different class, so it becomes a false negative one. And if we now count how many true positives and false negatives one, we will then able to select the tables like that. So there are 6 true positive, 4 false negatives, 2, if you just remember the example that I was showing. So we can fill these numbers here like that, and then we can come up with 3 measurement parameters. One is called the accuracy of the model, and that accuracy actually gives you how many true positives and true negatives. So true positives and true negatives are the correct ones. So we have successfully classified the green points and the red points, and those are there like 6 and 8, I think. Yeah, 6 and 8 in the numerator. And what is the total scenario? In the total scenario, we had 2 misclassified red points and 4 misclassified green points. So if we add all of that, then we take the ratio, we get the accuracy of the classification model. Similarly, we have another matrix called precision, and this computes the positive predictions only. So here it has correctly classified 6 positively, but there are 2 negative, 2 false positives. So in the precision, they take the ratios and identifies how many are positively, how many of them are positive predictions, and that gives us this number. And we have another parameter called recall, and here we focus on the false negatives one. So for example, how many of the correct incorrectly greens are in the red zone, and if we take the ratio, we get this. So these 3 are actually some intuitive parameters that we use when we compare different algorithms and different comparing different performance measures among algorithms. And we will discuss this in the tutorial. Okay, so yeah, we are finishing it. So maybe just a quick coverage on the unsupervised classification. So as we are discussing the supervised learning algorithms, where data were provided, where the training data has the labels on them. So for example, in the supervised learning, we may have such 4 clusters with 4 different type of classification labels on them. In the unsupervised one, we do not have the output or the target variables attached to that, and that will gives us to the figure in the right. And now the machine learning will be not as we were discussing, because we don't have the labels on that. We do not know whenever a new data point comes which belong to which cluster, and that's where it's get interesting to color these clusters based on some mathematics. And that's what basically the unsupervised learning to try to find the hidden structure within the data without the labels within that. And here first I'll discuss about the k-means. Actually, I will mostly discuss about the k-means, and the rest of the algorithms you can read it from the textbook. But they typically follow the similar philosophy. So in the k-means algorithm, it randomly selects a cluster point and decides that okay, this is the clusters, and then it try to find out whether it belongs to a better point or whether it can shift to a better point for average error reduction. And how it works is, actually I can show you that by an animation. So there are actually two steps within that. One is called the E step and another is called the M step. But the basic philosophy is that, let's say we are provided this unlabeled data, and we think that there are possibly two clusters there, and we start with two random points, and all the points we assign some values to those clusters based on that, and based on the values we find their mean. So here we assign the blue values in the second step, in the E step, and we assign the orange values. And in the blue values, if you just take an average, you will find another point, and in the orange values, if you take the average and if you take an average, you will find another point, and these two cluster centers moves, and then we repeat the same process again. Let me show you by an animation. So for example, here we have 4 clusters, okay, and based on those 4 clusters we can partition and we can color that, and then we can assign the center, and then we can shift the point to that cluster. And this is the first step. When we assign the points, and in the next steps we update the center. So previously the points were random, and now after assignment we calculate their average and we shift the points to the some location, and we keep repeating that till this whole algorithm converges. And this is an iterative one, and this expectation maximization is a very mathematical thing here. I'm not going into the details, but all the unsupervised classification, most of the unsupervised classifications are use this step. So in the GMM or the Gaussian mixture model, another popular one, they also do the same step, same algorithm. So assign the point, move the center, assign the point, move the center, and it keeps doing that, and till the algorithm convergence, and that's how it finds its cluster center. Okay, so there is something interesting happens. If you are lucky, you assign your initial clusters to the locations where you get a perfect separations among the clusters. That is happening in the left figure. But if you are unlucky, then you put the points in somewhere, then you get probably not good clusters. In unlucky initialization, it will catch the local optimum, and by the human eye you can see that the machine is not able to do that. So initialization do matter in terms of unsupervised classifications and in k-means, but we cannot do about that. So we can try multiple different initiation and hope to keep the best result, keep the best result. Okay. Yeah, so this is something. So here is the sum of the squared error concept comes into the picture. That's how way it actually calculates whether to align its center, and that's how it calculates the loss function. So once the cluster centers are close to the updated center, then that time this algorithm stops and it converges. And it can be seen that if you keep for a particular setup, different number of cluster values will give you different this error or SSE, where we can call it inertia. And then after that, even if you keep increasing the clusters, the inertia or the error doesn't go away, and that's this optimal point is sometimes known as the elbow method. Okay, but there are some drawbacks of k-means. So here is this is an unlabeled data. We call this like 2 moon data sets, and k-means try to find the clusters, but as you can see, it's not doing good there, because the decision boundary would be somewhere where these 2 clusters are different, but it is actually partitioning the space into a very weird, very weirdly, and it is not at all classifying them well. And in those scenarios, something called Gaussian mixture models and DB-scan method are useful. So in Gaussian mixture models, so if left is the scenario, then Gaussian mixture models can do some sort of this soft eclipse this classifications where k-means will fail there, and in DB-scan will actually do that clustering very well. Because it is a density based clustering techniques. So we in GeoAI we use a lot of DB scans often. for that. And this one applications for K-means is that it is used in image compression. So if you have 16 billion colors, you can actually do compress it to 8 using 8 colors only, and the image still looks like uh, quite relevant or quite equivalent. Okay, and last two concepts. How much time I have? I think I have 30 more minutes maybe. Quickly, I will cover the two quick important concepts. So we are basically seeing this weights as the parameters of a machine learning model, and there are other concepts called hyperparameters, and we will see in the tutorial how these hyperparameters plays an important role. So this is something how you design your gradient descent algorithm. So there was this concept called learning rate. So when you update the weight, how much you want the weight to be updated? Do you want them to update with a very higher value, with a very lower value, depending on that? And then in the SVM, how much you are allowing the width of the street, so that the points within that can be allowed to have contradictory labels or not. So these two concepts we'll cover in the tutorial, and then we will also cover what is the train test split. So means whenever we are doing the machine learning algorithms, we have the input data. We do not use all of the input data from that. We have a training data set, and then we test the model using a test data set, and we do not train the model using the test data set. And there is another concept called validation data set, which is very important when we do the hyperparameter tuning. So you can think of, you have given an input data, we split them into three parts. One is completely reserved for training purpose, another is completely reserved for test purpose. This test data doesn't see the training, doesn't seen by the model before training. And then in the training data, that is again divided into training and validation data. So in the training data, we train the model. In the validation data, we see how the model is performing. If we see the model is not performing well, then we tweak the model by changing the hyperparameters, and then we run that again on the validation data, and we keep doing that until we get good results from that. And how we do that, there is the diagram. I'll encourage you to revisit it. So basically we start with a list of hyperparameters, and we run the model, we check the performance. If we see we are getting unsatisfactory result, we change the hyperparameters, and we do that again on the validation dataset. So validation dataset helps you to tweak the hyperparameters, to tweak your model, and once you get good results, you then just test that model in the test dataset. And there is one concept called k-fold cross validation. So here I have been showing you one set as a validation data, but you can also do this. You can pick multiple validation set data, and you can do like multiple rounds. So for example, this is your whole training data set, and in the first part you pick 1/5 of that, and if you just divide that into 5 equal parts, in the first round you train the whole algorithm by the rest of the 4, f2, f3, f4, f5, and you validate that with f1, and you keep doing that for each round, but each time you select different chunk of the validation data. What it will do is that because you are mixing your validation data set, every time you will get a different hyperparameter, and that for each of those rounds, then you can select which hyperparameter is overall on in average performing you the best. So this concept is again implemented in the scikit-learn, or in the package we'll cover in the tutorial. But this is a very important concept when we try to update and tune our model. And of course, the last thing is that we need to do our data processing. So real world data is messy. They have sometimes like missing values. They have this, for example, you can have numeric and text together. You can have different values for the same city. So Helsinki can be written in different from this. Inconsistency can be there. There can be different numeric scales. So we try to get rid of those things before we pass the database to the machine learning algorithm. So they have continuous, discrete, categorical, and ordinal level. And There is another concept called one-hot coding, where we have categorical values. We try to convert them into numerical value, and this is like a binary representation. We use 1 and 0s for that. So red will be like 1 0 0, orange will go like 0 1 0 0, blue goes like 0 0 1 0, and green like 0 0 0 1. And in this way, we keep the categorical levels into a numerical one. And this is something we have also covered in the tutorial. We'll show that there is this concept of scaling. So if we if in an imaginary situation, if we know that, let's say, there is this midnight temperature, depending on that, in some part of Helsinki there are a number of cars in the road, and because they can be in different range, temperatures can be negative, as we know in Finland can be very cold at times, and then the cars are in positive numbers only. So sometimes they have influence on the data. So if you have very different type of ranges of data available in your data set, your model may perform differently. So we try to scale them in the similar range. So before normalization, they are in minus and plus ranges, but we can normalize them into 0 to 1. So this trick is called normalization. It helps a lot when you have variety of data within that. There is this also concept of like standardizing the data. But the important thing is that no matter what transformation we do, we need to understand that our end result will be in that same normalized, standardized way, and then we can revert back to the original number using a mapping function. Okay, so here is the one thing I missed actually. So standardization means you are putting the data into 0 mean and 1 standard deviation from. So if you see in the x-axis, it's minus 1.5 to 1.5, and it's centered around 0. So this is a statistical trick, sometimes helps us a lot when we deal with heterogeneous data. And here is the correct pipeline. So we need to first split the data, training, testing, validation. We need to fit them and then apply some transformation and revert back that transformation to get the correct output of that. And we have covered this entire pipeline in the tutorial, so we'll see it again. Yeah, I think I can. There is an optional topic, but I think I have a little bit time left for that. This is a very important concept. Sorry, I couldn't cover it in the tutorial, but I would encourage you to learn this concept. Principal component analysis, it's often help us to one concept called dimensionality reduction. So we have very high dimensional data space, and that will be very complicated for machine learning algorithm to learn if you have, let's say, millions of features, and it's not possible to use millions of features all the time. So you need to come up with you need to reduce the input feature space in order to maintain the computational complexity. In those scenarios, this PCA is very much useful. They are also used in image compression. Like they have many great applications. So I would just want to give you a very broad overview of how the PCA concept works. Is that, so let's consider you have a data that looks like a guitar in an X and Y data space. And each of those data space has two important properties. In the x-axis and in the y-axis, you can think of they have a mean and they have a variance. So for example, you can project each of the data point in the x-axis. You can take a mean, you get one value, and you can see that they are varied according to that space, is called the variance of the data space. Similarly, you can project each point in the y-axis, you can have a mean and can have a variance. And this mean and variance can be of, for x-axis, we can also have the concept of covariance for x and y-axis, and that's something mathematical. But what I'm trying to say here, without going into the mathematics, is that it is possible to do the standardization that we are discussing. We can align the data so that the data is mean around the 0, 0 points, and then we can adjust the variance. And once we do that, there is a transformation, or there is like the figure got little bit distorted. And the first thing is that if we now project all the points of the guitar into that 0, 0 line, we will get a straight line, right? If we just project to the y equal to 0 line, how it will look? We will look like this. This is something like a straight line. And does it covering the variance of the guitar? Well, to some extent, yes, it is covering how long the guitar is, but not exactly how long it looks, rather than the tilted version of the guitar. So it is giving us the idea that okay, the guitar is somewhat distributed, or the length of the guitar is somehow got twisted in that domain. But if we really want to measure how long is the guitar is, or how much it is the variance is, then we need to change the line from this flat line to something where the guitar is actually distributed, and that line is called the line of maximum variance. And this line actually gives you the idea of which way your data is most spread out. And if we now project all the data points to do with that line, and you can call that as a principal component line, you will get this line. So clearly this line and this line and this line are different if we project them together. So you can see the latter line where we had the tilted one, this one looks bigger than the straight line, and this is where the idea of principal component comes into the picture. So this is one axis in the data space where your data point are mostly spread, and this axis is called principal axis 1. And you can similarly get an orthogonal line from this line, and you can project your all points, and that will be your principal component 2. Now this principal components line actually gives you the spread of the data, where these data are, the spread of the variance of the data are, where these data are like mostly varied, and that will give us the capability to reduce or to identify those dimensions where we can keep most of the information from our data without losing much relevance. So if we have, let's say, 1 million features, and if we want to maybe want to keep the data into 10,000 features, so we will look for first 10,000 such features where we can see those variance is high. And that exact thing has been used to the image compression. So compressing correlated features, speeding up training and inference, and reducing noise before modeling. So I try to do this PCA for you guys to do the dimensionality reduction, but then there was not, like, it has been already been long. So I would encourage you go through the textbook, and there would be a lot of PCA materials available in the internet, so you can apply the same trick on the data, but that's an optional task for you. Okay, so here are the references. I think we are okay with the time. So here are the references for that, and you can check them from the slide. And thank you for your attention. We'll take a short break, and then we will start with the tutorial how to do that. But if you have any quick questions, you are asked to ask.
Thank you, Shubhra. Any questions from Teograd's side? No, I think they know everything already, so
Okay.
asking anything. Should we say 5-minute break and then go into the tutorial? So
Yeah. Let's have a quick break, and then we can start with the tutorial, because it will take some time to set up and do those stuff in the CSC environment.
Exactly. So the recording. Go.
Thank you. Okay. I think okay. Missing one student here, so let's wait a bit. He's coming back on.
Hopefully not coming back, I think.
Okay.
So we can
start. Okay, so if you guys have access to our website, then and if you are in front of a laptop, then we can go through it together. But you can of course revisit it again if you don't have a laptop right now. So if you go to the tutorial 1, so in the tutorials on the left, there is this lecture 2 after tutorial 1, basic ML tutorial notebook 1, where we first work with the classification data. We have used a simple Airbnb data for that purpose, so don't expect the accuracy results are too good, but they are somewhat good. But we have used this Austria Airbnb data for the tutorial, and I have tried to make as much as comment in the tutorial so that it becomes self-explanatory. If you don't have yet CSC account, you can still use the binder here on the top to run your notebook there, or you can download the environment and you can build your you can use Anaconda or Mamba or something like that. You can create your own environment. I have shared the YML file also. If you have CSC account, then you just need to click on the CSC notebook, launch CSC notebook, and it will directly lead you to the website. Yeah.
So if I try to log in through the Hacker account, it says the account doesn't exist.
Account doesn't exist.
So I don't think we have through Aalto any accounts in market.
Actually, we have. This is something actually I was not at all familiar, but I think we have sent the request to the CSC environment. So is it happening for everyone?
I haven't seen it.
I So you are not able to use your CSC accounts also?
I'm not sure
I mean,
if
like,
we do,
I
if we
guess-
have CSC accounts, if it's through another login thing, like through Hacker, when we go to Noppe, when you log into Noppe, then we use the Hacker login, but here in Mahti, it says we don't have any accounts.
Hey, Ivan, is it same happening to your students?
So do you guys, can you have, and has anyone tried to access this? It works for you? Because we, I think Farzad created for us the CSC accounts. So not the Haka. I know when you click on the link, it asks you to log in through either Haka, CSC, or something third, a third option. And we all have CSC accounts, so we actually can access the project.
Okay.
So do your students not have the CSC account, only the Haka?
I think there is this is something I am also not very familiar with, like, because for me at least, I can use both my CSC as well as Haka login. I'm just checking it. And for the students, I think it's a bit tricky in a way. So anyway, for today, we can still use the binder for the demonstration, but for the next time, I think we have to give it, we have to check whether we can give them the CSC access.
Exactly. So we are only using the...
Right, like everyone can. Sorry. And I'm checking my CSC. Let's see if I can give.
But is it right that your students only have the Haka login and not CSC?
Yeah, they have the. So you guys don't have the CSC login. They don't have the CSC login, but that's I think what we are trying to at least add the students.
Yeah, so Haka view to CSC.
Okay, now I see the problem. So basically, only Graz students are added here.
No, only the Graz students.
Yeah, I can see the members here.
Okay, so Farzad can update this.
Yeah, because he is the project manager. But what I can try at least.
Okay, so for the students, the update is that we will sort this out over the coming days and update you over Slack. So we have all your email addresses.
Yeah.
We just have to change it in the project settings with the CSC, and Farzad is in charge of that. So.
Yeah. I'll send him to Sunayana. Okay, so for this tutorial, so if we are not able to access to the joint GeoAI course, let's try to use the
Binder, yeah.
Their environment.
For me, Binder works as well, and it does everything pretty quickly, so that's fine.
So I think for the Graz guys, at least I can show you that if you click there, then you probably will get some interface like this, Jupyter for courses, right? And then if you select this joint GeoAI course, project 2018-216, there is a course module GeoAI course, and then you can give your working directory with your username. Just do that and then launch it. And for the Aalto guys, I will just encourage you, just click on Binder there. And let it run for some time.
So can you show us the next steps on the CSC, on the Mahdi? So after the session is
Started, yeah, and then you just need to connect to Jupyter. So do you guys able to see this?
yeah, they're nodding yes. Okay.
Okay. Sorry, my computer is somehow.
That's okay. They're saying yeah.
Okay, so if you just connect to Jupyter, then you will get here. And here within lecture 2, you can find the practical sessions, and there is a folder called lecture 2. If you click on lecture 2, and then you click on the tutorial 1 classifications, okay?
Yeah.
Just click on it. And I think
For the students, just one more question. This is the local copy of the notebook. So if they change something, they can't break the course.
they can change. They can change here. It's the local copy of their own. So they have it already create a repo for their own user account. So if they want to see this repo, if they go to here where they have this connect to Jupyter thing, they
Yes.
will go to this home directory.
Yes.
If you click on the home directory, and you will find one. So there is this, for example, this is my username, and you will find one folder called GeoAI. And then you will find a folder called practical sessions, and then you will see these codes within this folder lecture 2.
Okay. Cool. So this is
Just make sure you guys are in the same page.
so this is everything that they need to know about CSC. Good.
Exactly. So for the rest of the sessions, we will follow the same architecture. And so the Graz students, you can see the notebook from this setup, and for the Aalto students, you will probably it's running on Binder. So yeah, it's now. I hope everyone is now able to. So let's just do a quick check whether we are able to run this. So let's try to run all cells just to see that everything is running. So go to run here, and then just run all the cells just to see whether it is running completely in your computer. Fine. If any one of you are having some questions or some issues, let me know. I hope it should be fine running here. Probably it will take a little bit more time in Binder than because in Binder we need to install the packages. So yeah, at least in my computer it is running okay so far. So is it running okay, guys? Okay. I hope everything is good there. Ivan?
Yes. So far, yes.
So what I would do then, I will cover a little bit in the tutorial and for the classification, and let's see how much time we have. Because in the regression problem we have the same data, same everything, just the problem is little bit different. So I'll introduce it and you are encouraged to play with it. There are some scopes for doing the hyperparameter tuning and all those stuff. But there are two problems that we are trying to focus here. One is the classification problem. So I think everyone has successfully done it now. Ivan, I think everyone is successfully. Yeah.
The libraries are not.
Libraries are not.
I mean, it's just no module name, no file.
So
So for me, everything ran in binder. Okay. Are you guys all on CSC, or if somebody in binder? No?
yeah, we are in. We can just run the whole thing again.
Yeah.
We had a one small issue with one of the students. Yeah, I think now it should work.
Oh, yeah.
Working great. Okay. So we are, let's tackle the problem then. First is the classification problem, and first we show here is how the Airbnb data looks like. So you will see one data folder there in wherever you are working, and here. So in the first part of the lecture is just about the libraries, what you need to learn, what you need to report and all. So I'm not going there, but this part of one we will cover in the later, where we have this sklearn, the scikit-learn library, that is mostly the machine learning part. We will go it there slowly, and whatever, and some algorithms that we are discussing here is also there. But let's just understand the data first. What we have here is the Airbnb data. The source is listed here, and one visualization. So there are two files. One is the CSV file, where we have all the locations of different Airbnbs, their prices, their reviews, some other parameters like host, how is the host, or what's the response rate and all. And you can find the details in this website. And we are selecting some of the features from that data. And so first we want to check how the data looks like. So because here the data is inside the data folder, we can quickly scan that, and we can check that the data is within the data folder, the both of the data are present. And just to show you how it looks like. So there are some neighborhoods in German, of course, and there has some geometry. And in the CSV data, we can show like it, and we will see a lot of, yeah. So these are like some of the input features. There are many. So these are like the variables. So we will focus on two output variables. One is the price, but that will be considered in the regression problem, and another is the rating. So I think there is review scores or something like that. There is one parameter. It's below there. I will show you. Yeah. And after we do some pre-processing, we check the points on the map. This is very straightforward for you guys. I think all of you are from Geo, with some geography background. So we just plot them on the map, and then we define the classification task. So here comes the original part of the problem. So there are the goal here is based on this review score rating features. We create two classes. So this is a binary classification problem. One is whether it is highly rated or not. And we decide that because this feature is not there in the data, we decide that based on a cutoff value or a threshold value. And that value is 4.8. So how it looks? So if our rating is above 4.8, we provide the level 1 and highly rated. If the rating is below 4.8, we provide the level as not highly rated, and that like 0. So class 1, class 0, there are two such thing. Now the thing is that because this data is raw data, it's not clean data, there are a lot of discrepancies, there are some problems. There are, for example, some data features are like 95%, which of course machine learning algorithm won't be understanding. There are some cases where you will find the values like T and F, true and false. There are some places where you have this one bath or half bath or something like that, and these are not numeric features. So we were discussing about these categorical features and numerical features, but whatever the feature is, we actually have to convert them into some numbers. And for example, this price, you will find either this dollar sign or euro sign in front of it, and we need to clean that. So we created a helper function, and this helper function is applicable both in this tutorial as well as the other tutorial for the regression, where we process these values and convert them to some reduced to the numeric value. So how it works, for example, if you are providing as 95%, it will convert it to 0.95. If you are providing T on A for yes or no, it will convert it to 1 or 0. If you provide it like it just counts how many bathrooms you have, it disregards the text baths from that. Like that, we do that, and then it disregard the dollar sign in front of the box. So this is one part of the feature engineering that we do, the beginning, and everything is written here, how this function work, and so we define these functions here. Every function I have written some comments on that work, and in this part we map those functions for each such features, and these are the features that requires this pre-processing. And once we do that, we sort of engineer these columns from that features. So, and once they are converted into particularly numeric values, we then check the statistical measures of those features. So we can check how many times they are present in the data, what are the mean, their standard deviation, and their percentile, quartile, what is the maximum value, what is the minimum value. So just to check for yourself whether everything is worked so far well or not. Yeah. So this is one part of the feature engineering. And then what we do is that we similarly define our target variable, whether it's highly rated or not. So we provide that as an integer type here. And so we did some filtering. If there is at least 5 reviews available and that is not absent, then we do that, and then we try to plot how that distribution look. So in this figure, we see that there is this 4.8 line and something greater than 4.8. We are calling them as highly rated, and below that we calling them not highly rated. So there are this like approximately, this is the statistics of so many data points are highly rated, so many data points are not highly rated. And then let's just see some basic distribution of that. So we have plotted some. So this is just your playground. You can check their relationship with different input features, and then we can discuss about what type of features are actually there. We can categorize them. So there are numerical features where the values are numeric values, and please remember that we didn't include the output in the output value in the input feature. This will create data leakage. So just remember to, if you just know that the output value are not included here, but it's processed separately, not together with the thing. So the numeric features are here. Then we have categorical features. So numeric features will have numeric values. Categorical features, they have categorical values, and we can convert that here. we can like club them together in the x as a training data set, and in the y value we have provided the output value. Now here comes the train and state. So x is the whole data set that you have so far, and now we need to, before we build our machine learning model, we need to do the train test split that we are talking about. So this split will keep our test data separately from the training, and we will use the x train as our training data, and we will keep the x test separate. And to evaluate our model, we will use y test, and we will train our model using y train and x train. So x train is the features without the labels, the corresponding labels, whether they are highly rated or not, are contained in the y train. X test and y test will not be used in the training part. We will use them later to evaluate our model. And this is the command to do that. This part I will explain it later, but normally this I have written it here. So this is like when to maintain some balance, this command have been used, and random state is just a random starting point. So a random number is provided here. It's like a seed, so that every time you run it, it starts from the same randomization. Yeah, and then we just.
I have a question here, Shupra.
Yeah.
So how many columns are there in Y-train dataset or data frame, and how many are in the X-train?
So in the Y train there is one column, and in the X train there is this many columns. So all the numeric features and the categorical features. So if you print them here, okay, I can actually. That's a good question, Ivan. Actually, I should. And print the.
Because Y-train are basically the labels, so maybe we can just print out the X-train and Y-train so that students can see what are the features and what are the labels. That's what I'm getting at.
Yeah. So yeah, this is the thing. So I can maybe put the train. So if I print it, so you can see there are 23 features here. So there are 23 columns. There are 6,664 data points. And in the Y training set, we have just one column. So, and then same goes for the test data sets. So, and then if we just break the features, we have these numerical features and we have these categorical features. Is it clear, Iman? Or I should write it in a different way?
Yes. And what are the values in the Y training?
They are just 1 or zeros. So I can actually make. So this is the X train. So this is all the features you can see. And if you just similarly print the Y train, you will see either zeros or ones. Yeah.
Okay.
Okay.
Using each feature set or each row in the X train is basically one property with all the different features and the feature values. Yes. And then the Y train is basically the label 0 or 1 if it's a highly rated or not highly rated property.
Yes, exactly.
So just want to make that very clear for students who haven't done machine learning before, so we can continue.
Yeah. Actually, you are right. I should have shown this more clear way.
Sorry for the interruption. That's fine.
No, you're absolutely right. I thought like this is quite straightforward, but actually it is not. I should have made some visualization for the data. But just to make sure that I am providing to cell here. Sorry. just to give you the idea. So if you print the X train and Y train, you see there are 23 columns in the X train, and these are the features or the input features. And you can see there are some values are numeric, some values are not numeric, and this is because these values are categorical values, and this is because then we have the numeric values that we have. And in the Y train we have the 0 and 1. So this is like one column. So based on this one sample, we define whether it's a highly rated or whether it is not a highly rated one. That's what we are trying to train the model on. And then we will in the next part, we will provide, in the test part, we will provide the X test, and it will be same 23 features, but our model will not use the output of these features. Our model will directly use them to predict the Y test, and this Y test is what we will use for compare what our model predicts, and that's how we evaluate our model. So I hope this is now clear. So just know that the machine learning algorithm will take this X train and this Y train as a pair, and it will then predict whatever X test you provide to it, and then we compare the result of the X test with the Y test. So there are 4 things. I'm repeating again. We have split the data into 4 components. X training, that is the 23 features training data set, and each of those sample has a label assigned with it, that is called Y training. This is something our machine learning algorithm will be using for training purpose. Once the machine learning algorithm trains, then the task of us to provide the same algorithm with the test data, where the test data will only have the 23 feature values, but they are not labeled. And the machine learning algorithm will then predict the values for those test data, and we will compare those predictions with the true level of those test data. That is Y test. I hope it is a bit clear now.
Yeah. Great.
Yeah. Okay. I can probably add a table here so that you can, if you can refer back to it and see it in a clear way. And now, as you can see, we are almost ready, but not fully ready, because there are these categorical features here. These are text, and the machine learning algorithms won't be able to process this text, so we have to convert them into numerical values. And you can also see there are this concept, there is this thing called KNN, which, so we in computer we call this as not a number, and these are some missing values. So we need to impute these values also. So because if we just pass this to the machine learning algorithm, either they will ignore it or they will provide some errors. So here in the slide I was talking about some data pre-processing. Here basically we do that. We do the imputing for missing values, we do the scaling, and then we do the encoding for the numerical for the categorical values. And that we do using a concept called column transformer. So because these are all columns of a data frame, so we convert each column or transform each column in a similar way, so that we can convert both on the X test and the X train. And there is a way of doing that. Just to remember, so this is the like just to remember, this is like the 2 basic categories of the columns. One is the numeric column, one is the categorical column. We use the column transformer to convert everything into the numerical, because the computers cannot process the categorical one. And yeah, this is something you can read. So this is just the same thing. What is the test data set, and why we don't provide the test data set. The whole data set we need to split it before. So the what order is here, we split the data into train and test, and then we feed the pre-processing. We do the training set, we train the model, and then the same thing on the test set, and then we evaluate. That is like the pipeline. And this whole pipeline thing is used by so there is this function called pipeline. I will show it here. That takes care of the processing. So start implementing one algorithm so that it becomes clear now. Okay. So first, the idea is to build an logistic regression algorithm, and we will use these two concepts, pipeline and the column transformer. So what we will first create this function, okay, where we have the steps within it, and so you remember we are talking about the pre-processing. So there is this imputer and scaler. So imputer, the role of imputer is to identify where the data are missing. For example, we have seen one NaN value in the data set. So it will find out the missing values and it will use the strategy called median to fill those missing values, and then it will use the standard scaler to scale those data. So scaling is something what we have discussed in the theory, and these are the steps it will go. So it will look something like this, and here there is some description that you want to read if you want to know how these things actually work in Python. So every time we need to pass, we can do this manually instead of using this pipeline, but that will be a very repetitive manual laborious effect. So rather we create such instances so that we can pass directly this to the data so that it can automatically take care. So now one thing is that here you can notice for the numerical one, we can directly use the imputer and scaler to fill the missing values and to scale them. But for the categorical feature, we cannot do that because the categorical feature, we don't have the numerical value. So we need to do the one-hot coding. If you remember, we are talking about this one-hot coding where we had different colors and we were converting them into 1, 0, 0 or 0, 1, 1, something like that. And this is the idea is to convert them into numerical values from categorical values. So we built two transformers. Sorry if it is a bit confusing, but if you just read through it, it's very clearly written. So we built two transformers, two column transformers to convert the categorical variables to numericals one and converting the numericals one and scaling them down. Both of them have this imputation step. So where we have the missing values, either we do by most frequent or we do by the median. And then for the numerical one, we scale them. And for the categorical one, we do the one-hot coding to get the numeric values. Once we are ready, we have these two pipelines ready, and the description is written here. Then we build a preprocessor, and that is where we put the recently built transformers in one place, so that we use this all together to these 23 columns of the X-train data and X-test data. So this numeric transformer and the categorical transformer that we are talking in the up, we put them together and we provide the numerical features and the categorical features that we were discussing above. So here, if you remember, we had these 23 features. Here we had these features. So this thing now goes to this column transformer. So we have the column transformer, we put the numerical features and the categorical features together, and then we define the logistic regression pipeline. And after this thing is done, we define where exactly the machine learning algorithm is done. So in the preprocessor, we put the column transformer and we define a classifier here, and this is the logistic regression. And this is the iteration that we are talking about for the log functions. You can provide some value here, you can play with it, but more number of iterations means it will take longer time to convert, and that's how the pipeline is complete. But I think it's very confusing here, so that's why I encourage you to read how the thing works and in one single picture. So here I have written one block diagram So we have the raw Airbnb data. We had two types of features in that data. One is numerical features, one is categorical features. What we did with the numerical features, we made a numeric transformer. With the categorical feature, we made a categorical transformer. What those transformers does, both of them either fill the missing values by median for numerical one or fill the missing values by most frequently occurred ones. Then they scale the missing values, then they scale all the values using the standard scalar method. And then if the feature is categorical, then they do this one hot coding and they convert the text to 0 and 1. Once we do this pre-processing, they come to this column transformer into a single data set, and then they pass to this logistic pipe. And this logistic pipe is nothing but the main machine learning classifier that takes the pre-processed data and produces the and learns the pattern. So how it works now, let's look at in the next part. So what this whole machine learning is about, running these two important commands. So either you can use the pipeline that I showed you, or you can directly use a machine learning algorithm here and then fit. Using this fit command, you can pass the training and the trace data. So remember that this is something logistic pipe. That instance I am showing you is may look a bit complicated, but you can directly use the machine learning algorithm here, just this one, this logistic regression here. So you can just directly copy this and use it here, and the main part is after what is happening. So when you use this command fit, it starts training. And how it starts training? It starts training by using the X train and the Y train. So if you remember, X train is the training data training table, which has 23 features, both the numerical and categorical features, and Y train is the 0-1 level. And once you use the fit command, the algorithm learns, and then you can predict after passing the X test. And this predict doesn't include the Y test. Why? Because that is the goal of the machine learning algorithm. It will not use the Y test here. It will only use the X test, and whatever it predicts, we save it into a variable logistic.pred here we are saving. And then we will check what is the accuracy score now. Whatever, so I have already covered this accuracy score, precision score, recall score. There is another variable called F1 score. I didn't cover it, but sometimes it is used. So you can just check it here. This course is also important in some context, but mostly we use in the confusion matrix these three: this accuracy, precision, and recall. And this is the matrix that we can create based on these functions. These are already provided in the scikit-learn matrices. And what we are doing here, in each of these matrices, we need to pass two things. What are those two things? One was the ground truth of the test data, that Y test thing that was already created from the data set. And what is this thing? This is what our algorithm predicted. So this logistic pred is being predicted here using the X test values. We just compare how accurate our predictions with the real values in the data. And then we come up with the scores, and here we can see the score is written here. Do you have any confusion or questions so far? Or is it a bit okay? Or it's confusing? Sorry guys. Graz guys, are you following me up to here?
Yeah, I think students are following. Yeah.
Okay. Okay, and then this is something like the whole flow. Okay, so where we have the train test split done, and then we have the testing data reserved for this. We played with the training data, we prepare the pipeline, we fit the training data, and then we use the test data to predict here. We have the prediction, we compare the two answers, and here. So I have made it like a block diagram. If you get confused with the terminologies, just revisit the tutorial again. I hope everything should be fine. And we can now create this confusion metric that I was talking to you about. And because logistic regression gives us the probability, so I have also draw a probability distribution. If you want, you can explore more, but you can ignore. But the main thing is that we can now build the confusion matrix. So there is this true level and the estimated level and the predicted level. So if the true level is 0 and the predicted level is 0, then something like this happens. If the true level is 1 and the predicted level is 0, so this is the way we get the true positive, true negative, false positive, false negative. That the concept I was showing you in the theoretical class. So now we have seen this for one algorithm, this logistic regression. Let's assume now we have multiple algorithms we want to build the model. So do we do this for every algorithms, or can we actually come up with something more useful or something more convenient? So we can actually evaluate multiple models together using a reusable helper function. So how we can do that? We just create a function and we use the same pipeline concept inside that. And in that way, what we can do, we can use a list of models and compare their accuracy. So I can first maybe show you this diagram. So we have shown these decision trees, and the k-nearest neighbors, they can also do the classification task. And I have kept the random forest and SVM for the assignment. So just focus here. We are only showing the 3 algorithms. So we have the inputs. So dictionary of models. So we have multiple models that we want to test. We have some preprocessor and we have the training and testing data. And for each, and we do that in one go. For each loop, we create a fresh pipeline. We fit the pipeline on both train data. We make the prediction on the test data. We calculate the accuracy, set the matrix, and we do that by repeating here. And this is the function that I have created for. So it gets the models, gets the preprocessors, it gets the training and test data within it. And what it does is that for each model here, creates the pipeline, it trains, it predicts, and it calculates the accuracy score. And it does do the same thing for all the models together. And how to use that? You can use that by, for example, we have now 3 models. Classification are done by 3 models. One is the logistic regression that I have shown already. We have the KNN and we have the decision tree. And in the bracket, these are the hyperparameters that you can change, that you can tune with the cross-validation part. So this is the depth of the tree that we have covered in the lecture. This is the how many samples in the leaf can be. There is the iteration for the loss, and this is the number of neighbors that can happen in the KNN. So we have 3 models here, and in these 3 models, we run the same pipeline, and then we can see that these models can be used to come up with different accuracies, precision, and recall score. And we can plot them. And the good thing is that you don't need to create manually every time. Or if you want to add one more model, you just put that one more model here. For example, if you want to do the SVM, you just write, okay, I write SVM. I will take the SVM classifier here. I think it's called SVC, but I will not write it down because that's in the assignment of the thing. But you get the idea. So we can just keep adding more models here, and we just pass it to the same iterative loop, and then we can get the accuracy of the same model instead of running or writing the code every time, the same code. And yeah, and then we can just similarly create the confusion matrix for all those models. That is here. And sometimes we are also interested to learn that which feature is more important for the model to come up with the accuracy scores. And there is a function for that feature importance. So I think here, yeah, feature importance function. So for the decision trees, at least it can give you the feature importance. So this is a very optional thing. You can explore it. And then I created this hyperparameter playground. So this is for KNN. As we know, different number of Ks can affect your accuracy. So this is some values I have created for Ks, and just to check like which value gives you different accuracy. So the idea is to run the same pipeline, just to loop it around the different K values. So for each K values, you run the same pipeline, you fit it, predict, and then do it, keep doing it. And then check the accuracy score. You can see some up to some value of K, the accuracy was increasing, but not much. And this gets interesting with the decision trees. So this is completely optional thing. You are encouraged to play with this thing. So for example, for the decision trees, as we were discussing, depth of the tree will have a very important role, but there is the problem of overfitting again. If you get it too shallow, then it gets underfitted. It gets underfitted. If you get too the depth is too high, then it gets overfitted. So here we will play with that. We vary how large is the tree for the depth. Here we are varying it from 1 to 6, so 16 or 15 actually. And if we keep doing that for different value of the depth, we get different accuracy running the same algorithm. And you can see that the test accuracy was increasing up to a certain part, and then it starts decreasing. And which is the exact thing that we're discussing about the bias variance trade-off. So at up to a certain point, and it will give you good test accuracy, but then it will start decreasing because the model have been overfitted with the maximum maximum number, the high depth of the model. So far this is if it is clear to you guys, or do you have any questions, or part of it looks confusing? Okay. I guess not then. And similar way, we have the regression problem now. I will not take much of your time. I'll quickly. Yeah. So can you guys try again with the run all cells with the regression one, and just check whether it works or not?
So in the classification exercise you just showed in the notebook, you didn't actually use any spatial information about the
We use the latitude and longitude actually. So
okay.
Yeah,
so there were features as well, but not very high on the importance list, I guess.
Yeah, so basically you can see the latitude has a higher score than the longitude. So that means in Vienna, at least the price has some, or the rating has some influence on the latitude rather than the longitude. At least the data shows in that way. And they are not bad in terms of importance. I think in the regression problem, we will see the more effect of that.
Yeah.
At least. So we start in the regression problem. Everyone is able to run this? Think? Yeah. Okay. So in the regression problem, we have a different agenda. We start with the same data pre-processing, same helper function as we did in the classification problem. We do modify the values. We do some filtering. We plot them, and then we select our target variable. And now here our target variable is the price of per night for one for each of those Airbnbs. So let's have a look at the plot. So if we have the raw data And this is for tutorial purpose. I find that the price are very much skewed, and you can see the box plot is very much skewed. So I filtered it so that we have a better data for visualization purpose. But that's what happens mostly. You will have a lot of outliers, and the machine learning will have a problem. Algorithms will have a problem to fit a good regression line on this outlier with the data with these outliers. So we need to get rid of those outliers in the occasion depending on the problem. Here we are actually getting rid of those outliers because of the skew. How we get rid of the outliers? So you can see this is quite unrealistic pricing, like $10,000 per night. I don't know how this millennial will stay there, but not us. So we'll just get rid of those outliers here, and how we do that, we use this technique called IQR. If you are interested, you can just have a look into this part, but it's just to know that we are getting rid of the higher values and just keeping some lower values, and 75% of the lower values are there. So there are four quantiles, first, second, third, fourth. We are keeping them up to the third quantiles, and that's how we create the upper fence. And then we just restrict everything within that upper fence. And if we now look at the map, we can see that everything is now come down to the around $250 per night, which is reasonable. And if we do the visualization here, you can see those high priced Airbnbs are quite centered around, and then in the peripheral there are some low priced Airbnbs, which is typical urban structure. And we can now check the histogram of the data distribution. So you can see the same plot now looks better. The skewedness has gone, and there is this beautifully looking a little bit skewed normal distribution here. You can play with the data. Here is the box plot of the data, of the output data. So this is our output data now. So previously in the classification problem, we had this output data 0 and 1. Now we have the output data as the price, and we are going to use the same features, same 23 features that we used in the classification problem. And so we start doing the same data pre-processing steps. We divide them into numeric features and categorical features the same way we did in the earlier classification problem. Then we did the start. So yeah, you can see the number is a little bit different here, the training and the testing data set. I think we have excluded two features here. I think I did that on purpose to show you some errors on the, so to show you some implementation of the region lasso regression. So previously we had 23 features. I think this time we had 21 features. That's why the data set is not exactly the same number, but you get the idea. So no, there are 25 actually. Sorry, I have added 2 more features. I think here we had 23 features. Check quickly. Features in that classification problem. Sorry, yeah, there are 23 features. Now we have 25 features. So two more features I have added here to make it somehow it increase the regression scores. Yeah. Okay, so here what we did is the same idea of doing the numeric transformer and categorical transformer, and that's what exactly we did in the earlier one. So numeric transformer, what it does, it imputes based on the median, it scales the data. So there are 2 steps in the numerical transformer, and in the categorical transformer, it imputes based on the most frequent data, and it do the one-hot coding. And once we transform them, we provide them inside a pipeline as a preprocessor pipeline, and that preprocessor basically transform these column values to they apply the numeric transformer to the numeric features, they apply the categorical transformer to the categorical features. Once we do that, we are ready with our preprocessor. This preprocessor transform our data, our training data and test data as well. And then we import our linear regression model and we apply that linear regression model after the preprocessor and we thus create the pipeline. So the pipeline will now take care of the preprocessing step and then the linear regression step, and that's how our pipeline looks. So we have the transformer, we have the categorical and numeric transformer, then we have the linear regression after end of the transformation. And because now it is a regression problem, we will use two different error matrices. One is the mean squared error, another is the R2 error. And these two matrices are just squaring the, checking the differences between the predicted value and the output, the true output value, and squaring that. That's how the name suggests, mean squared error, and taking the mean for all the data points. So we now use the same. We also defined another RMSE. So this is the root mean squared error. If you take the mean squared error and take the square root, you get the RMSE. So we have 3 error measures. Now we do the same 2 important steps for any machine learning algorithm. We use the trained data to fit the model. We use the test data to predict the model output, and then we use the prediction to calculate the scores. So here we calculate the R2 score, RMSE scores, and then we display this here. So this is for one model, and you can see this R2 is the correlation coefficient. So if it's some over positive, then it's so there is a positive correlation with the data points. It is coming as 0.40. The more it goes towards 1, the more it's better. And if we now plot it, the actual versus predicted price, we can see there is some relationship exists here. At least there is a tendency of, if the actual price goes high, the predicted price will also go high. And then using this similar concept of the way we built the pipeline before, we use a helper function, and where we can use multiple models together. So this is the same code that you can use, and here the idea is to use, I think I have used the decision tree, linear regression and lasso regression together, and for the assignment probably you have to implement the random forest and what else, I think random forest and another something, Ridge regression is there for you. So yeah, so as you remember, here are multiple models, and each model will have some hyperparameters within that. So for example, in linear regression, we didn't provide any hyperparameter, but if you want, you can provide the learning rate for the gradient descent. So that is something new, you can play with that. I didn't provide it here, I made it simple. For lasso regression, if you remember, there is this penalty term that we talked about. That is exactly what this alpha is about. And for lasso regression, this is different. For this is same for ridge regression, but the values are a little bit different. So there is a playground here I have created for you. You can check, just tweak the different parameters, different values, and check how the error looks like. And then we have decision tree regression. Similarly, we have different. We can play with the maximum depth of the tree as a hyperparameter. And this pipeline works similar ways. We have the regression models. We just put it into the pipeline, and it takes care of everything, and it gives you the errors here. The errors. So you can see that most of the models, they have similar RMSE. So I think the better performing is the linear regression. So lasso regression has they are similar, but lasso regression doesn't perform well. Linear regression, the basic model perform the best here, and decision tree has a little bit higher error here. So yeah, when we can plot them, these errors, we can see the more R square value means it's better fit, and we can keep playing with that. There are these plots from actual price and the estimated price. And this is the concept of residual. So this is just the difference between the what is your model is predicting and what is the actual value. So instead of doing the square, you can just take the difference. and you can then plot the histogram. That's why these residuals can exist in negative, but your sum squared error cannot be negative because that is a squared term, so it will be positive all the time, and the loss. And this decision tree we can again use to do the feature importance, which feature is more important. As we can see, there is little bit, this number of bedrooms has a heavy influence on the price. That is quite, I think, intuitive to follow. If you have more bedrooms, that means you have more price there, and then you have other features accordingly. So here we can see also the longitude has a more effect rather than latitude in terms of the price importance. And there is the hyperparameter playground for you guys if you want to play with it. So for example, I have created different values of alpha for our lasso regression, and you can check that different alpha values will give you different error. And you can see that as you increase the alpha, the error is actually increasing. So you can test for different values of alpha for that, and same we can do for decision trees. And it will be really interesting if you want to implement the gradient descent and check for that value of the learning rate, how that influences. So for example, the decision tree, we can check the depth of the tree. So here we have different depths of the tree, and we have the RMSE, and we can see that that interesting thing is that the test error again goes down, and then after a certain point it starts again increasing. And if you remember, this is the same bias variance trade-off thing that I was discussing. So initially you have a very shallow model, you don't have much depth, and in that part you have high error, like the RMSE is high. As you start complicating your model, your RMSE is going down, 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 and up to a certain point your RMSE is actually very less compared to the other ones. And then if you keep increasing the complexity, it starts to overfit, and then the error goes, the test error goes high. So that is sort of the, so here it is the summary of whatever you have learned so far. And this exact tutorials will be helpful for you to do your assignments. All you need to do is to understand how the models work, and then create the different two other models in the assignment. So in the assignment, you have to probably implement the SVM, random forest, and for classification, I think you have to implement the regression and random forest. So if you understand the concepts, you can either use the pipeline that I have shown you, or you can just simply use the models instead of this pipeline concept. But I think if you are really want to build complicated ML models, it's a good thing you have the knowledge of this, how the pipeline thing works, because for complicated deep learning models, this will be really helpful for you. So yeah, thank you very much for your kind attention. I know it's a bit complicated and confusing maybe at places, but I have tried my best to write this thing so that you can anytime revisit and take your time and take slowly and can learn it from that. Yeah, if you have any questions so far or feedback, it's super boring.
Questions? No, then thank you, Shupra, from the TU Graz side.
Thank you, Ivan, for coordinating it.